Okay. Oh, okay. So I guess we are ready for starting our next session. And the first speaker of this session will be Maitraya Bhattacharyya, who will be talking about neutrino transport in binary neutron star mergers. So take it away.
Thank you. Yeah, so I hope all of you can hear me. So yeah, hi, I'm Maitraya. This is my first time at your university, so thank you for inviting me. So I am a postdoc at Penn State working in David Radich's group, and I mostly work on algorithm development for GPU-based codes concerning neutrino transport. So I'm going to talk today about neutrino transport in binary neutron star mergers with our new numerical relativity code, AthenaK. So this is work for the past almost three and a half years that I've been doing with David, along with a couple of other collaborators. So let's begin. So I think the problem that we want to look at numerically is the problem of the binary neutron star mergers. And this slide is roughly gives you a summary of what we understand about these type of mergers. So what we have at the end is where you have two neutron stars, which are sort of in spiraling, and they sort of merge and usually form some kind of remnant with some accretion disk around it. So there are various parameters on which the evolution of these neutron stars depend upon. I think, for instance, the masses of the neutron stars and also the spins of the neutron stars. And besides this, you also have a nuclear equation of state, and this largely determines how things turn out in the end. I think one of the most important parameters in this type of evolution is the mass scale of the equation of state, which in our case is essentially the maximum mass for a non-rotating neutron star. And depending on the masses of our binaries, we can sort of qualitatively try to predict what the outcome will be at the end. So when the sum of the masses of the two neutron stars is much larger than the mass, the reference mass, we essentially have merger happening, and then the neutron stars will promptly collapse to this black hole in vacuum. If you have the masses, the sum of the masses maybe equal or a little less than this reference mass, you would have a remnant neutron star forming, which is unstable, and this remnant can sort of be short-lived, or it can also be long-lived, and it can, at some point of time in the future, it collapses to this black hole. It depends on various factors what actually happens. And then, of course, you can have the sum of the two masses much smaller than this mass. And there is then a possibility that the resulting object is just a stable neutron star with an accretion disk around it. So these are the type of systems that we would like to study. But why would we like to study them? I think one of our main motivations here is multi-messenger astronomy, especially this event, GW170817. We want to study them because we can actually see them. And this particular event is one where we had, in addition to gravitational wave observations, also, observations along the whole spectrum of EM. So we had multi-wavelength observations in gamma rays, X-rays, UV, optical, infrared, radio, and so on. And this type of event is, you expect to see more of these events as the accuracy of gravitational wave detectors improve, and also as you have more and more number of these. And this can actually allow us to probe various questions in fundamental physics. So I think, one of the things that we're definitely interested in is, these transients, these things just popping up in the sky that you can see. And so this is the kilonova would be the optical part of the result of an event like this. And you essentially expect to see for several days, maybe a month, for a very long time along these various spectrum of EM, these observations, because gravitational waves are not typically, gravitational wave detectors are not typically accurate to observe maybe the merger and the post-merger. So the evidence of the merger and the post-merger is typically reflected in its electromagnetic counterpart. So the hot merger sort of unleashes this flood of neutrinos into the ejecta, and the neutrinos are essentially important to control this neutron to proton ratio within this ejected matter. And this ratio sort of ensures what type of elements get created, whether they're light or they're heavy. And in the composition of the ejecta determines what kind of color, what you essentially see in the kilonova. And this sort of process explains the blue and the red light seen in the kilonova, like the one from GW17017. So besides this, we would also be interested in understanding where do this stuff come from, especially the origin of heavy elements. So, I mean, it has been said that core collapse supernova is not sufficient to actually form very heavy elements in the universe. And as an alternative, a binary neutron star system or binary neutron star mergers have been proposed, because so instead of the usual process, the proposed process, this is called R process, nucleosynthesis, or this is called rapid neutron capture. And what happens here is essentially you need some seed nuclei in an environment which is very rich in neutrons, such that the sort of seed nuclei, the seed nuclei and the neutrons can actually interact with each other to form these very heavy elements, which are unstable, and then they undergo beta decay. And this is an important phenomenon that we expect to see in these binary neutron star systems. So, and then there are other motivations. For instance, they have been short gamma ray bursts also have a connection with binary neutron star mergers. And finally, neutron star systems have been proposed as a source for the formation of these high mass black holes. So neutrinos sort of dominate the thermal evolution of the formed disk. And essentially, neutrinos become very important in the merger and the post-merger phase. And when you have an accretion disk, neutrinos are sort of important for controlling the cooling of the disk. And since they change the proton-neutron composition, they can change the composition of elements in the ejecta. And that will essentially change how what you see on Earth. And besides neutrinos, pair annihilation, pair processes have been proposed as one of the factors that drives the relativistic jet. So this is also this makes sense for us to then have neutrinos in our neutron star simulations. Now, in order to sort of model systems like this is actually a neutron star system done in Athena on the GPU. However, this does not have neutrinos yet. So the type of things that you want to have if you want to simulate these systems on computers is you need to have Einstein's equations, which sort of solves for the gravity. I mean, the talk right after mine will discuss this in greater detail. And then you would also need this nuclear theory-based equation of state. You would need electromagnetism, because MHD is important if you want to simulate these neutron stars. And finally, you need some treatment for neutrinos in the simulations. So you would have some kind of transport for the neutrinos, and you'd need to do something to describe how these neutrinos sort of interact with matter. So at Penn State, we are working on a couple of things. I am personally working on classical transport. So I'm working on full Boltzmann methods in AthenaK. I'm also working on the method of truncated moments, or M1. And this is work currently ongoing. Besides this, along with collaborators from the University of Trento, we've been working on this GPU-based library for neutrino-matter interactions. This is called BNS New Rates. And we've had a first application with this library that came out earlier this year. And so this is essentially what forms the right-hand side of the equations of transport. And it's open source, and it works on both CPUs and GPUs. And then finally, we are working on introducing quantum effects and neutrino oscillations in our simulations. And this is work that is being led by a graduate student of Penn State with a first application to BNS mergers that came out earlier this year. So having neutrinos in the simulations is important, but also having accurate modeling of neutrinos is also very important. And this plot sort of demonstrates this. So this is from a very old paper in our group. So what is seen here is this histogram of electron fraction and the specific entropy Barbadian and the angular distribution of the ejecta in a BNS merger in some snapshots. And what you have are simulations that are done with different types of treatment of neutrinos. So HY, which is the blue line, is essentially when you just have hydrodynamics and no neutrino treatment. And the LK, which is the red line, has only neutrino cooling and the effects of neutrino cooling. And M0 has some treatment for neutrino cooling and also for neutrino heating. And you sort of see that if you look at these plots, you see that these results actually vary substantially. And so accurate treatment of neutrinos in these simulations is probably essential. So here comes AthenaK. So AthenaK is this new code that is developed at Princeton and other places, including Penn State. And AthenaK sort of proposes to be this general purpose astrophysical code, and it's the successor to the very popular Athena++ code for GPUs. Athena code has this block-based AMR driver doing octree mesh refinement on Cartesian grids. It has support for general relativistic magnetohydrodynamics using these finite volume solvers. It has support for a full Boltzmann photon transport scheme on geodesic grids. It has support for the equations of gravity, the Z4C formulation of the equations of gravity. And finally, we are building support for neutrino transport using the truncated moments formalism. And also, we have developed certain tools to do finite element and spectral type discretizations for full Boltzmann methods. Finally, we are in the process of providing first-class support for neutrino opacities using this library BNS New Rates. So the difference between Athena++ and AthenaK is essentially the K, which stands for Cocos. And Cocos is this open source C++ library for performance portability. Cocos is a Linux Foundation project, and it's completely open source. And the entire point of using something like Cocos is we want to have code that sort of works across various types of hardware. And the way Cocos achieves this is instead of using standard C++ constructs, you use abstractions which are provided by the Cocos library themselves. So for instance, instead of using a raw multidimensional array, you use something called Cocos views. And instead of standard loops, you have something called Cocos loops or Cocos parallel loops. You similarly have mechanisms to do reductions and so on. And the idea is that the project provides various underlying implementations depending on different types of hardware. So you have implementations for CPUs, you have support for NVIDIA and AMD and Intel and so on. And the idea is if you're using pure Cocos things in your code, if Cocos supports a particular platform, your code is likely to run on that platform with minimal modifications to it. So this write one, run anywhere kind of philosophy that Cocos has which is why we use this now, because a lot of the supercomputers in this country are moving to GPU-based machines, and we need to find a way to sort of run our simulations on these machines, including these two big ones, one which is AMD and the other is Intel. And So, I mean, the entire point of using GPU-based machines for our purposes is because the Boltzmann transport solvers are actually very expensive. And so our solution to solving a full Boltzmann type of approach is to throw a lot of GPUs at it. And if the code scales reasonably well, we still expect to get sensible results within a finite amount of time. So just to give you an idea of what the equations for neutrinos that we have to solve. So the main equation here is just the Boltzmann equation. And the Boltzmann equation essentially describes how the distribution function for neutrinos changes. And so the distribution function essentially gives you the number of neutrinos at a given position moving along some direction. And this is essentially the expression. So df d tau, where d tau is just the affine parameter in phase space, is equal to some collision term. So I mean, it's important to note here that the distribution function is not just a function of position, but it is also a function of the momentum of the radiation carrier. So the resulting PDE that you get at the end of the day is a 7-dimensional partial differential equation. So the idea is things would move along geodesics in phase space. It will not move along geodesics if there's some matter and the radiation carrier sort of interacts with matter. And what makes Boltzmann transport of neutrinos different from Boltzmann transport for something like photons is just this collision term. It's just a different way of sort of expressing how the radiation carrier is interacting with some matter. So essentially, the Boltzmann transport, just writing this down, so the number of neutrinos at a given point in space is changing with time because the neutrinos have some velocity and it's sort of moving away from that point with that given velocity, or because there's some force which is acting on the system. It could be any type of force. And also because neutrinos on the right-hand side are getting absorbed, or they're getting created, or they're getting scattered. Now, for the sake of simplicity, we sort of try to solve this equation in this orthonormal basis space in a frame that is co-moving with the fluid. And the reason why we try to do this is because the collision terms, the interaction terms between neutrino and matter sort of become simpler if you do it in that frame. So the equation that we will solve for the rest of this talk is this equation highlighted in the box at the very bottom of the screen. The gammas are just the usual Christoffel symbols, and p mu is just the momentum of the radiation carrier, and so on. So just to give you a quick idea of the right-hand side of the Boltzmann equation, this is, let me just give you a brief idea of the library BNS New Rates. So BNS New Rates is a performance portable library for neutrino-matter interactions, which also makes use of the COCOS framework, although New Rates is an independent project and not a part of Athena directly. So this is work done in collaboration with the University of Trento and Penn State. And the idea of BNS New Rates is essentially that we don't want to have tables because it's hard to interpolate results from a large multidimensional table on a GPU. So instead, we have fast computation of the kernels of the reaction on the fly without using any sort of table. We have also support for higher Ls in the reaction kernels. So it's the library has support for reactions with a certain degree of isotropy. So not only is this good for an M1 type approach, but we also are planning to support a full Boltzmann kind of approach where you have all the angular information that is available, and hopefully you have more accurate opacities. So New Rates also has support for a Python interface, and this is something that we have used for post-processing BNS runs, so it can work in a variety of scenarios. The type of equations that are currently implemented in the code are very standard beta processes, with effects for mean field and weak magnetism. And besides this, we have electron-positron annihilation reactions, nucleon-nucleon Bremsstrahlung reactions, then isoenergetic scattering on nucleons, and finally inelastic scattering on electrons and positrons. So we have a first application with this library for BNS mergers. This was mostly done, post-processing snapshots of BNS, post-merger simulations using, Einstein toolkit-based, THC code. And the plot essentially is trying to determine, how each reaction sort of contributes to that snapshot in post-merger. So what we have here, what we are plotting essentially here is the absorption opacity or the scattering opacity, depending on the reaction, as a function of matter density along two different directions. I think one was the x-axis and the other was the y-axis. I think probably the dashed line is probably the dashed line is the z-axis. So essentially tells you how each of these reactions contribute to the final post-merger part of these BNS runs. And the library is actually sufficiently performant. It's been optimized to run well on GPUs. So if you look at some performance plots on the right of the screen, you essentially have the zone cycles per second, which is a measure of how performant it is as a function of mesh block size. So mesh block is essentially a quantum of the grid of AthenaK. So for instance, 64 just means you have 64 cube points and so on. And we sort of see that if you have sufficient number of points, the GPU variant of the library actually outperforms the CPU variant by almost an order of magnitude. And these numbers are good enough for us to use this in production without having tables. So there are various ways to solve the equations of transport. And well, one category of methods I would just call approximate methods. And the reason why we want to have them is because because the equation is 7-dimensional, it's just expensive to solve a PDE like that. And so you'd want to solve an approximate equation instead. And I think the first models were these phenomenological models, these neutrinos leakage schemes. And then you have something called the method of truncated moments, which instead of solving for the full distribution function, solves for the first two moments of the distribution function and makes an assumption for the other moments that it is not solving for. And of course, the accuracy depends on how well you're able to approximate the higher moments. And then, of course, you have full Boltzmann solvers. For instance, you have Monte Carlo methods. You have method of discrete ordinates, which sort of discretizes the angular part of these equations in these discrete bins in angle. You can also use spectral methods, different way of discretizing angle. So instead of you use real spherical harmonics as basis functions in angle, you can also have finite volume schemes. In fact, there is a project inside AthenaK which uses this. And finally, you have finite element in angle, sometimes called FEMN. And finally, hybrid schemes, which sort of use a combination of these approximate methods and Monte Carlo methods, using the Monte Carlo method as a more accurate way to have the closure for the M1 when things are actually not good for M1. And so I will mostly be talking about the M1 scheme and the filtered spherical harmonics and also the finite element in angle. I mean, there are talks tomorrow which will go into further detail on Monte Carlo methods and also on the M1 plus MC type schemes. So this is actually a port of the M1 that we have in THC. This now works on GPUs. So just to give you a summary of the moment method implemented in AthenaK, the main thing to do is to take the Boltzmann equation and you just rewrite the Boltzmann equation as a set of evolution equations of the moments of the Boltzmann equation. So you sort of take the momentum and you have a portion of the momentum along the direction of the velocity of the fluid, and you have the other part which is orthogonal to it. And you can use that information to actually compute J, which is the 0th moment or the energy density, and H alphas, which are the radiation flux, and then L alpha betas, which is the radiation pressure. And you sort of can write the stress energy tensor for radiation as a sort of using the moments of the distribution function. And you can sort of write them in any frame. So for instance, you can use the N alphas, the normal on your slides to actually write them in the rest frame of the fluid, but you can also use it to write it in any frame, including the frame that we prefer, which is the frame which is sort of co-moving with the fluid. And once you write that down and you have this conservation of stress energy tensor, you end up with equations that look like this, which tell you how the 0th moment and the first moment evolves. Now, there is nothing really approximate about these equations. These are exact. The main problem with solving the M1 is that although these are exact equations, they are not complete, which is to say that if you look at the right-hand side of both these equations, you'll find things like PIK, which is essentially the radiation pressure. So if you have complete information about how radiation pressure behaves, then these would be exact, but you don't have that. And therein lies the problem. So you would need to solve another equation for the radiation pressure, and that would have a higher moment, and so on and so on. So what you want to do is, just to make things simpler, you say, I would like to assume that the radiation pressure takes a certain form instead of actually solving this. So the way this is generally done in an M1 solver is, you know that in the optically thick limit, sort of radiation and matter are in equilibrium in the co-moving frame. And then you can sort of write down the radiation pressure in terms of J, which is the radiation energy density. And you sort of know that in the optically thin limit, radiation is sort of directionally propagating in one particular direction. So you sort of know how the radiation pressure should behave in these two limits. And the approximation is essentially, let's try to have some kind of interpolation between these two limits. You just do a combination of the optically thick pressure and the optically thin pressure. With this factor, this 3 chi plus 1, the chi is just called the Eddington factor. And this is just computed with this flux factor, which is a function of the radiation energy and the radiation flux. So you're sort of essentially saying that the radiation pressure can be written in principle in terms of the first 2 moments of the distribution function, which is not exactly true. So this approximation is not really good in regimes which are not optically thick or optically thin, but it is a choice that we make because the equations are relatively easy to solve in this formulation. So, as I said, for certain types of systems, it may still make sense. Like if you're doing supernova experiments in 1 dimensions, you might still have a good handle of how the pressure behaves. But for a binary neutron star merger type of system, this is not necessarily the case. So what I have here is a plot from Richards 2020, which is sort of just showing a snapshot, a side snapshot of this central object on the disk. And so I believe this is a Monte Carlo code. And what essentially is plotted is just the Eddington factor and the flux factor. So you sort of know that in the optically thick limit, the Eddington factor should have a value of 1/3, and in the optically thin limit, the factor should have a value of 1. And the color is essentially what you get from a Monte Carlo type method. So this just tells you how many cells have that particular value. And so as you see, that things at the 2 ends are still relatively fine, and things in between are not too bad, because the black, which is like most cells, sort of behave in this way, and the different lines are just different types of closures that were used. But then you also see that there is some kind of spread. So in general, you cannot just use the 2 moments I mean, there is some problem here in certain regimes. So you might want to sort of improve how you predict what the pressure looks like, and people have tried this in various scenarios, and one of them is something we haven't tried, but this is something that is out there, which is this data-driven approaches, which sort of tries to map the energy and the flux moment to the pressure using machine learning type algorithms. And there are algorithms which sort of still preserve some physics when it tries to construct the radiation pressure. And this is something we have not tried, but it seems like if you have a full Boltzmann solver, you can sort of use the information from the pressure moment of that exact solution to sort of inform how the approximate method should behave. So this is something interesting to look forward to in the future. So just to give you a very quick idea about the full Boltzmann solver that we have in the code, this is still very much a work in progress. We sort of just write the Boltzmann equation down explicitly and just notice that there are these p mu hats. So the hat is essentially the frame which is co-moving with the fluid, and L mu hat are these tetrad quantities that sort of transform from the rest frame of the code to the co-moving frame of the fluid. And so essentially what we do is just take an ansatz for the distribution function, which is a function of this f, which is just functions of position. And then you have some psi a, which is some angular basis function. And then you have chi n's, which are some energy basis functions. Just generic basis functions, I mean, we'll choose specifically later on, and you just put it, you sort of substitute it into the Boltzmann equation and just integrate over phase space. And so at the end of the day, what you have in this formulation is just a set of advection equations. And these boxes, these yellow boxes, are just matrices which are integrals of energy basis functions. And these are something that you can pre-compute before you even start the simulation. And then you have these blue things, which are also matrices, which are functions of the angular basis functions and derivatives of the angular basis functions, also something that you can sort of compute at the beginning of the simulation. Now, you sort of can pick and choose your basis functions to derive different types of schemes. So for the finite element type approach, we will choose a specific basis function that I will describe now. So the angular part of the Boltzmann equation, of the Boltzmann system, we try to discretize using geodesic grids. And one of the reasons why we sort of use geodesic grids is because internally in the code, every vertex, which corresponds to an angle theta phi on my grid, is just represented in Cartesian coordinates. And we like Cartesian coordinates, and we'd like to avoid singularities at the poles. Also, the elements of a geodesic grid are roughly equilateral. In fact, when you have the base grid, which is just a regular icosahedron, they are exactly equilateral. But when you do refinement, they are almost of similar areas. So the base grid, you start with a regular icosahedron, which is my base grid, and the vertices correspond to the angles, and they're sort of lying on the surface of a unit sphere. So this grid would have like 30 unique edges and 20 equilateral triangles. And there's a very simple way to actually refine grids in angle using this strategy, which is just you take some triangular element of the grid, you find for every side of the triangle, you find the midpoints, and you just project the midpoints on the surface of the unit sphere. And that's it. So this can help you go from 12 angles to 162 angles to 2,562 angles. It's a very straightforward way to actually sort of refine in angle when you're sort of solving for the Boltzmann equation. And we now sort of define basis functions on this grid. So when we talk of finite element methods, we just have linear finite elements. So the basis function just looks like that. So it's an overlapping tensor. So on the geodesic grid, you have at a particular point, the basis sort of is 1, and then sort of linearly becomes 0 at the neighbors. We call it overlapping tensor. So if you wanted to have something like an SN type scheme or discrete ordinate type method, you would have basis functions that look like that, which is just like pentagons and hexagons on the geodesic grid, and they're not overlapping with each other. So let's call it the non-overlapping honeycomb. And we sort of see that when you have basis functions that look like this, which is that there is some sort of overlap between neighboring basis functions, you tend to reduce something called ray effects. And ray effects are these blob-like unphysical solutions that you sometimes see when you use discrete ordinate type schemes. So this particular example, you're expected to see sort of a smooth shell. And I have 642 angles on this grid, and also the same thing on that grid, but you sort of see these blob-like things instead of a very smooth, cylindrical shell of radiation. So this is one of our motivations to using these overlapping tent type basis functions. Now, instead of using something like a geodesic grid, in that same formulation, you can also choose to just have the angular basis be real spherical harmonics. And then you have what is called the method of spherical harmonics, filtered spherical harmonics, or FPN. So you can use a full Boltzmann code to actually have, in a hacky way, also have an alternative way to do moments. So the way this works is there is a relationship between the modes of the solution of the full Boltzmann scheme and the moments of the solution. So if you wanted to use a full Boltzmann scheme to just do an M1, what you would essentially do is you notice the connection. So for instance, the L equals 0 modes of the filtered spherical harmonic scheme corresponds to the radiation energy. The L equals 1 corresponds to the fluxes, and similarly, L equals 2 corresponds to the pressure. And so the idea here is to, if possible, even as a sanity check, we would like to do M1 and full Boltzmann using the same code. If you wanted to do that, what you would essentially do is you would evolve an FP1 type of scheme, which just evolves the energy and the radiation fluxes if you convert it in that way. And then you use, once you obtain the energy and the flux from your FP1 solution, you can just estimate what the pressure is going to look like using an M1 closure type approach. And then instead of evolving the pressure, which is the L equals 2 mode, you just substitute that value. So this is a way of sort of doing M1 using full Boltzmann type schemes in the way we formulated in the code. So I'm just going to quickly show you some results that we have. And so the first test that we have here are these ray effects, tests for ray effects. And so what this test essentially does is you have a cylindrical beam of radiation at the origin of your domain, and the radiation is propagating isotropically with time. So what you should essentially see after t equals 1 is this shell of radiation that is propagating with the speed of light, and then sort of radiation sort of decaying as you go inside. So the plot here on the left is just the exact solution, and what we are plotting here is just the energy density. And just as a comparison between the different types of methods, so if you use a finite element type of scheme with 642 angles, this is what the solution looks like. It's not as blobby as the one with the discrete ordinate type scheme. And then if you were to use something like M1, that's the solution, which is not great, but M1 doesn't do very well in this test. So this is another test where the M1 solution sort of fails, and because the reason why it fails is because the M1 method actually cannot distinguish between different sources of radiation. So when you have two beams of neutrinos interacting with each other, the solution that you expect to see is the solution at the very right of the screen, which is the beams go past to each other and they just go their own way. And finite element type of schemes can sort of reproduce this, but sometimes it is very difficult to resolve the beam very finely. So you need to have a large number of angles to actually get results which look reasonably okay. If you use spherical harmonics, filtered spherical harmonics, this test just fails. Like it has a very hard time when it comes to positivity preservation. It's just, we use filtering to remove oscillations from our solutions, but in certain tests, it is impossible to actually get rid of areas where you don't have negative number of neutrinos. So this is a problem of the method with this test. Just to give you an idea of how these methods perform when you have complex geometries. So I have a grid, I have a source term. So we now have this finite. So the right-hand side of this equation is actually not zero. So you have a source term, and the sources are generally quantified by three numbers. Eta is called the emissivity, it's a measure of how many neutrinos are getting produced. And then you have kappa A and kappa A, which are the absorption and the scattering coefficients. So we have a grid with sources that look like that. So you have this central emitting kind of square, which has some emissivity, some non-zero emissivity, and it also has some scattering coefficient. And that thing is sort of emitting neutrinos in all directions. And then you also have these white squares, which have some absorption coefficients. And then you have everything else, which is blue, which has some scattering coefficient. I just want to give you an idea of what the tests look like when you have a toy source like this in a complicated kind of geometry. So the first result that we have at the top row of plots is essentially when you evolve the system to about t equals 3.2. So this is roughly the time that should take the radiation to reach the edges of your numerical domain, but not enough time to reach the four corners of the numerical domain. And you sort of see that the methods do reasonably well. However, the discrete ordinate type solution does show some ray effects, which is what you see, these ray-like things sort of going out. But then if you evolve the solution to steady state, you see that the methods are sort of comparable to each other. Similarly, just to give you an idea of the M1, this is something called the shadow test. So the shadow test is essentially where you have a beam of radiation that is entering the numerical domain from the left, and you have this cylinder at the center of the numerical domain with some scattering opacity. And what you should essentially expect to see is the beam sort of hits the cylinder, and the cylinder casts a shadow behind it. And this sort of gives you an idea that the M1 is working in a somewhat sensible way. So we also tried playing around with different types of sources, maybe a slightly more realistic example where you have this sphere which is emitting radiation. In this case, this is not a sphere, this is a cylinder which is sort of emitting radiation. And you sort of try to see how things behave with different types of schemes. And we see that in almost all cases, because you have like this discontinuity at the surface of the cylinder, that is exactly where you expect the error to be large. And increasing the number of angles or increasing the resolution of the simulation does not necessarily cause a huge difference to the error. So we sort of see that if you look at the steady state solution, things like filtered spherical harmonics actually do a very good job. So the filtered spherical harmonics is just the middle column, and you see things. I don't think. Hang on. Yeah, so the filtered spherical harmonics should be the column, the top right. Essentially, things look very nice as you'd expect it to see. But then you see all the other methods have these sunflower-like things coming out of it. So, and the sunflower-like things do go away, but when you increase the angular resolution of your simulation. But this is something you have to keep in mind. Some methods perform better than other methods in certain types of test problems. And if you have a system which is almost spherically symmetric, and if you have a robust way of handling oscillations in your spectral code, filtered spherical harmonics might give you, more accurate results at a lower angular resolution. So this is essentially the conclusion from this test. We've also tried looking at things when the medium is moving. And so, for instance, this is a case. This is a very simple 1D test where you have a medium which is moving with a velocity of 0.5 the speed of light, and it moves till time t equals 2. And you have radiation, a Gaussian pulse, which is sort of fully trapped with the fluid and sort of moving with it. And what you should essentially see in this test, which is this black line, which is this Gaussian, which is sort of moving and it's sort of also diffusing a little bit. And we try to compare the exact result with the finite element scheme and the filtered spherical harmonic schemes. In fact, all schemes sort of agree with the exact result. So things are not looking too bad when the medium moves. Similarly, we also sort of tested how things look like in our M1 code when you have a non-flat background. So I'm just showing you M1 in this plot because you need a lot of angles to actually do beams nicely. So the M1 is essentially, so what you have here is a Schwarzschild black hole, and then you have a radiation. This is coming in from the left. And what you should expect to see is the radiation sort of just bending and following the geodesic. And so the geodesic is seen in these dotted lines on both sides, and you sort of see that it's following that path. So we have a fairly good understanding of. I mean, we do think the M1 code is working as you'd expect it to. So this is roughly all that I have now. I'm just going to probably end here. And so what we're currently doing now is we're sort of coupling the M1 solver that we have in Athena with BNS new rates, and this is currently being tested on GPU-based machines. And once hopefully the coupling is done, we expect to do a BNS with an M1 type transport, hopefully sometime later this year on GPUs. So I mean, thank you for listening. So AthenaK is an open source project. It's available at the GitHub repository, and there are a couple of papers coming out of it. AthenaK is also completely developed in the open. So the commit that was made yesterday is already there for people to see. BNS new rates also operates on the same philosophy, and yes, also open source and works. Both the projects are licensed very liberally under BSD3 clause, so it should be fairly easy for you to use them. Also, maybe integrate the library into your codes. So thank you very much for listening, and I will take any questions you have.
Any questions? And please repeat the question for the online crowd.
Yeah, I've got a quick question. So I've already got a copy of your AthenaK and BNS new rates. But the thing I was curious about is to get access to the latest THC and M1 codes and other things. Is that also on GitHub? Or I know that David's got a website for your group at Penn State where he has put out current versions of all sorts of new updates, but I'm wondering, where is the other code located? Is it still at your group website, or you have to go to GitHub now to get the latest versions or everything? So definitely this stuff is on GitHub, but the other parts are software.
So I will have to get back to you. I think at one point, yeah. So the question is, sorry, the question is where can you get THC online? So I will have to get back to you. I think we were.
Contact with David early on back in 2017, and we did get the latest versions of the THC code that your group was working on back then. But where is it located now? Because we definitely want to get up to date on things and try code out.
Yeah, so I think we had a Bitbucket at one. Yes, there should be, like the latest version should already be public. I can send you the link.
I think it probably should get in touch with you guys again and follow up on this, but we want to definitely find out where you're at on this research right now. There's a number of things we're working on here, which might be of help to your group on a very advanced plasma physics stuff. We're working with Phil Morrison's group in the Institute for Fusion Studies here on very advanced high energy, high density plasma research, which might be very valuable to this particular. You're using existing GRMHD type codes, whereas Phil's group is working on very, very advanced PIC code stuff to do high energy, high density plasma physics, and we'd like to try to put that into this area to see how this helps maybe on the plasma physics side of this. But we definitely want to catch up on what you guys are doing on all.
Thank you.
So on the slide where you were doing the test with the two beams comparing with the spherical harmonics and the M1, I was just curious about why with the spherical harmonics there's like this white region down there, and like why does it not resolve things?
Yeah. Yeah. So the question is, why do you actually see this white region in the plot where two beams are intersecting with the FPN method? Yeah, I think the main issue is just positivity preservation. So So, I mean, it's a spectral scheme. We have some filtering techniques and some rules of thumb to choose the strength of the filtering, but sometimes things are not adequate when you don't have a substantially high number of angles. And I mean, so I did not show the M1 in that test because the M1 sort of fails, because if you have two beams colliding, they sort of become one beam after they've done so. So the M1 doesn't work.
Thank you.
Thanks.